Hey guys, welcome back. You only have 2 lessons left in this unit. I know it's been a little bit of a doozy because there's been a lot of math, but hopefully today will seem like a little bit of a break because we're doing something called mole ratios. And mole ratios, in my opinion, are a little bit easier. There's not quite as much thinking involved with them, so I'm hoping you'll find that the ending of this unit is a little bit easier as we go to review for our test. So without further ado, let's go ahead and jump into it. So first of all, what is a mole ratio? Well, a mole ratio is just the comparison of the coefficients from the balanced chemical equation. So how many moles of what compound are equal to how many moles of another compound in a chemical equation. It basically just tells you the relative amount of each compound or element in a balanced equation. So when we write ratios, there are different ways to do it. So you could do it with a colon. So this would be like a 1-to-1 ratio with the colon in the middle. You could write it as a per, so as a fraction, or we could write it as like a fraction where you have the numerator and the denominator. So each of these would be a correct way of writing a ratio. So when we take a look at mole ratios, sorry, I went a little bit too far ahead there. When we take a look at the mole ratios, we're just comparing how many of each type of compound or element we have in the balanced chemical equation, okay? Now, these are going to come from balanced equations. So as we see here, we've got 2 equations. Both of them are totally balanced, and some of these compounds have coefficients, okay? So basically what we're doing is comparing the coefficients, okay? So let's look at some examples. So like if I asked you to tell me the mole ratio of N2 to H2 in this particular example, you would just compare the coefficients. So there's this assumed 1 in front of the N2, and there's a coefficient of 3 in front of the H2. So our mole ratio there would just be 1 to 3, okay? Because there is 1 N2 for every 3 H2. Okay, so here we're really just comparing the coefficients, so it's a little bit easier. So if we want to compare the N2 to the NH3, again, we're just looking at those coefficients. There's a 1 in front of the N2 and a 2 in front of our NH3, which is ammonia. So that would be a 1 to 2 ratio. And then finally, for our comparing our H2 to our NH3, we've got a 3 in front of that H2 and a 2 in front of our NH3. So that is going to be a 3 to 2 ratio. Okay, so for every 3 moles of hydrogen gas, we're going to have 2 moles of ammonia, which is NH3. Okay, that's all we're doing here is comparing the coefficients in the equation. So now let's look at this one. We've got 4 aluminum, 3 oxygen will yield 2 aluminum oxide. Okay, so again, we're just looking to compare the coefficients. So if we're looking at the ratios of aluminum to oxygen, 4 aluminum, 3 oxygen, that would be a 4 to 3 ratio. Okay. Now, what about aluminum to aluminum oxide? We've got 4 aluminum for every 2 aluminum oxide, so that would be a 4 to 2. And again, anytime we're doing anything with coefficients, that can actually reduce to a 2 to 1. So if you notice as you're doing these fractions, if they have a common factor that they can be reduced by, go ahead and do that. So 4 and 2 are both divisible by 2, so that will give us a 2 to 1 ratio. And then oxygen gas, O2 to aluminum oxide, it's just a 3 to 2 ratio. Again, these are pretty easy because we just have to compare the coefficients in front of the compound. Okay, so when asking for the ratio, we're just looking for the coefficient in front of the compound or the element. Okay, now we can use this to help us solve problems. Okay, so because they're set, mole ratios can be used as a conversion factor, right? So this is a conversion factor we can use to determine moles of one substance from moles of another substance, okay? So let's take a look at some examples here. So the first question says, what is the NO to NO2 ratio? Well, that's easy. We just have to look at the coefficients. So in front of my NO, I've got a 2, and in front of my in O2, I've got a 2. So that's a 2 to 2 ratio, which can, of course, be reduced to 1 to 1, right? Because 2 is divisible by 2, which gives us 1. So for every 1 mole of NO I will have 1 mole of NO2. So my next question that I can now use to help me solve this problem, it says, suppose you have 20 moles of NO. How many moles of NO2 could you produce? Well, because it's a 1-to-1 ratio, if we have 20 moles of NO, we're also going to have 20 moles of NO2 because it's the same amount, right? It's just a fractional problem. We're just relating the ratios to each other. So then let's take another look at an example. The O2 to NO2 ratio. So O2 is a 1 here. And then NO2, we've got a 2. So this ratio is a 1 to 2 ratio. That means for every 1 mole of O2, we're going to have 2 moles of NO2. So our next question says, suppose you had 20 moles of O2. How many moles of NO2 could you produce? Well, it would be double the amount, okay? Because for every 1 mole of O2 you would have 2 moles of the NO2. So 20 times 2 is going to give us 40. So for every 20 moles of oxygen gas, we're going to have 40 moles of NO2. Okay? So again, just a fractional problem relating our moles to each other. So let's take a look at some more examples. It says if you used 1 mole of P4, how many moles of pH3 could you produce? Again, this is going to be a ratio problem. So there is 1 P4 for every 4 pH3. So you'll have 4 times as many of the pH3 as you do of your phosphorus. So if we have 1 mole of the P4, we would just wind up having 4 moles of the pH3. Okay? Then the next one, if 12 moles of pH3 were made, how many moles of P4 would be required? Well, this would just be working backwards, right? So if we start with 12 moles of pH3, we know that there are 4 moles for every 1 of our phosphorus, so you would just have to divide by 4 in this instance, which would give us 3 moles of our P4. Okay, and we will set this up like a conversion factor as we have done with our other fractional problems. So we start off with what we know, which is 12 moles of our pH3, and we want to end with our moles of phosphorus, so our P4. So if we do that, we will set up our ratio, which is 1 mole of P4, which comes from our coefficient, 1 mole of P4 for every 4 moles of pH3. 12 divided by 4 is equal to 3 moles. Okay, so again, these are just conversion factors using our mole ratios. Okay. If 6 moles of H2 were used, how many moles of pH3 would be produced? So we've got 6 moles of H2, and then so it's a 6 to 4 ratio. 6 and 4 can both be reduced by 2, so it's a 3 to 2 ratio for our H2 to our pH3. So if we do a 3 to 2 ratio, you basically just multiply by 1.5. So 6 times, or you should divide by 1.5, I should say. So let's set it up like we do this one. Let me do it on the annotation really quick so we can see this one. So if I'm going to set this up, I start with what I know, which is 6 moles of my H2. And I'm going to set up my mole conversion with my mole ratio. Okay, so this is H2. And I want to get rid of my moles of H2, so I'm going to set up my conversion with my moles of H2 on the bottom, and then my moles of pH3 on the top. So then if we do our mole ratio of 6 to 4, which again reduces to 3 to 2, for every 3 hydrogen, or H2 we have, we're going to have 2 pH3. So then this is just a fraction problem. So 6 times 2 would be 12. Divided by 3 will give us 4. And that's how we get that answer right there. Okay, so that's where that 4 moles of pH3 comes from. All right, and then that final one, if 0.3 moles of pH3 were made, how many moles of H2 were required? Same thing, we're going to set up our conversion factor using our mole ratios. So for every mole of pH3, we're getting rid of pH3 and we're going to H2, so we want to have our moles of pH3 on the bottom and our moles of H2 on the top. And again, you could do this as 6 over 4, or you can go ahead and reduce it to 3 over 2, which will give us 0.45 moles of H2. And again, how you would solve this, you would do 0.300 times 6, and then divide that answer by 4. Okay, it's just a fraction problem. So let's just do a couple more examples here before you guys move on to your independent practice. So here we have a balanced equation. So N2 plus 3H2 will yield 2NH3. So our first question here says, how many moles of hydrogen gas are needed to react with 6.5 moles of nitrogen? So these are worded a little bit differently, but again, we're just going to use our conversion factors and we're going to do these step by step how we know. We start with what we know, right? So we have 6.5 moles of nitrogen. So that's what we're going to start with. So we're going to start with 6.5 moles of nitrogen. Next, we're going to do our mole to mole ratio. We're going to use our ratios as our conversion factor. For every 3 moles of hydrogen, we have 1 mole of nitrogen, right? So 3 to 1. This is just coming from the coefficients. Then you will just multiply through the top. So 6.5 times 3 divided by 1 gives us 19.5 moles of H2. Okay. Again, when you're setting these up, just because we're using ratios here, we're still setting them up to where we want the unit that we eliminate to go in the bottom and the unit that we want to keep goes in the top. So the H2 goes in the top because that's what we're trying to get to. And when you ever see, anytime you see these diatomic molecules like N2 and H2, those are in a gaseous form. All right, so B says how many moles of ammonia would be produced if 4.5 moles of hydrogen gas were used? And again, ammonia is NH3, so it's asking about NH3. So again, we're going to start with what we know, which is 4.5 moles of hydrogen gas, and we're going to set this up to do our mole ratio. So we need to know how many moles of hydrogen are there for every mole of NH3, and it's going to be a 1 to 2 ratio. We're going to put our gas on the bottom. So our 1 will go on the bottom because we want to eliminate our hydrogen. Oh, I'm sorry. Hydrogen gas, not nitrogen. Hydrogen is 3. So it's a 3 to 2 ratio. So our 3 will go on the bottom to eliminate our hydrogen gas. And then our 2 will go on the top for our ammonia. So 4.5 moles of H2 times 2 moles of NH3. Again, this is just the ratio from the coefficient, so a 2 to 3 ratio. That would give us 9, and then 9 divided by 3 moles would give us 3 moles of NH3. Okay, and then finally, how many moles of nitrogen are needed to produce 5 moles of ammonia? Same thing, start with what we know. We have 5 moles of NH3. We're going to use that mole ratio. There's 1 mole of nitrogen for every 2 moles of NH3. The 2 will go in the bottom because we're eliminating the NH3. Okay, remember the number and the unit always stay together. So the 2 will always be with the NH3. The 1 will always be with N2 and 3 with H2. Okay, so 5 times 1 is 5. Divided by 2 is 2.5. Okay, now these are very similar to what we did in the first part of this unit. Okay, it's just that finding the mole ratios are pretty easy because we just have to look at the coefficients in the balanced equations. The only thing that I could think of here that might get us tripped up is if we're not putting the ratios in the right place. Okay, always